Hi everybody. So this is our first video over the orange equations, and now we'll be getting into one-dimensional kinematics. As you can see on your screen, we're going to start first with 1D kinematic equations. Now, first we want to write the three orange equations, and what we have to use are these variables off to the side here. Oh, I don't have an orange. Let me find orange. Is that orange? Ah, that's orange. Okay. So we have these variables. We have initial and final position, initial and final velocity, acceleration, and time to use for these equations. Now, we will write the three orange equations first to get started. Now, the red equations, I will write those up top so we can see like the progression as we go through the kinematics. So red is v bar or v average equals acceleration times time. Let's clean that up. Okay. And the other one is v bar equals change in position over change in time. Now, the orange equations kind of get more complicated from that. So let's start with the first one that has to do with change in position. Okay, so we have delta x equals, so we've got v naught t plus 1/2 at squared. And I said that we would be using the initial and final position. I already made a liar out of myself. So we're using change in position there, which I guess you could say this equals xf minus x naught, to put it in those terms. So that's our first orange equation that has to do with position, velocity, time, and acceleration. But there's no, so if you notice there are some things missing in that equation, we'll go over that in detail in a minute. Now, next we have let's see, the final equals v naught plus at. The final velocity is your initial velocity plus the acceleration and multiplied by the time after that initial velocity was measured. And I'm going to have to erase these so that I can fit that third equation in there. But those are the first two orange equations. So if you need to pause and write those down, pause and write those down real quick, and I will erase these to fit the third one in there. Okay, so our third equation is vf squared equals v naught squared plus 2a delta x. Okay, that one's the more complicated of the three orange equations. Now, why do we need three equations instead of just one equation that told us everything? Well, each equation is missing something, like I mentioned before. We'll talk about the third one since I've already got it written up here. The third one, let's see, it has v final, has v naught, it includes the positions, and it has acceleration, but there's no time involved in that equation. Now let's see, let's say we go to, we'll just work backwards. That was the third equation. Now let's go to the second equation. Get rid of all that. Second equation is v final equals v naught plus at. Okay, we've got v final, v naught, a, and t, but we're missing the position in that equation. And then if we go to the first equation, there we have delta x equals v naught t plus 1/2 at squared. Here we have position, v naught, acceleration and time, but we're missing v final. So you can see, given the scenarios or given your givens, depending on what you have to solve that problem, you can use a different orange equation. There is no one equation to rule them all when it comes to kinematics. Sometimes you've got one given that's missing, sometimes you've got another. If you have all of your givens, then you can use any of them that you choose. That's just up to your discretion. So the reason we need 3 equations is because each equation is built to solve for different things, and each equation is also missing something. Now, the third question is, what is the major limitation of these equations? Now, if you noticed, we have initial velocity, initial position, final velocity, final position, and then we've got time. We don't really break time down into initial and final. That doesn't make a whole lot of sense. But acceleration, there is no initial or final acceleration in this. Orange kinematics assumes that acceleration is constant, which is not always the case. In real life, if we're studying a real scenario, it's not uncommon to have a constant acceleration, but you don't always have constant acceleration. So that is a major limitation of the orange kinematic equations, is that it assumes that you have a constant acceleration in your scenario. So let's continue on to find some examples. So first, why is non-constant acceleration a problem? So first, let's draw these graphs as we go through this. So all 3 orange equations are built from this one concept, that acceleration, constant acceleration, is v final minus v naught divided by t. Now, I just said constant acceleration. That's not what I meant. I meant average. This is average acceleration is v final minus v naught divided by the change in time between the initial and final scenario. So this A is an average acceleration for the time interval delta t. Now let's graph that. I'll use orange. So a constant acceleration on a v versus t graph. That means that it is just a line. And that line could be anywhere. It doesn't matter really given our scenario right now. So I'll just draw a line. Get rid of that. That's constant acceleration. It's negative, but it's constant. Constant acceleration on a v versus t graph will always be linear. Now, it might also be flat. So if we put this up here, let's bring that straight to 0. If we have, it did not cling to the ruler like I wanted it to. There. So it might be flat. That just means that its a slope is 0, meaning the acceleration is also 0. But for constant acceleration, you will always have a linear graph. Now, let's see what a non-constant acceleration would be. Usually, a non-constant acceleration is going to look like this in our scenarios that we will have in this class. We will usually, if it's non-constant acceleration, parabolas are about as complex as we get. But now you can see that this non-constant idea can become an issue if all we have is these orange equations, because the orange equations make an assumption that we're dealing with a straight line. As soon as that straight line starts turning, the orange equations blow up. They don't work after that. Now, we will be able to deal with non-constant acceleration later. But with just the orange equations, which is pure algebra, we cannot work with anything that's got non-constant acceleration. So for the rest of 1D kinematics, for chapter 2, we will try to stick to mostly constant acceleration, but if it changes, you will need to use the power rule or take a derivative. Now, average velocity. Average velocity is assumed when we derive the hardest orange equation. So the hardest orange equation we have is v squared equals v naught squared plus 2a delta x. Oh, that's still covering stuff. Let's put up there. So we'll start with the two average velocities and average acceleration. So this is average, and this acceleration we know also to be average. So if we start with these three equations, we can derive that third equation. It's the hardest one to derive. So first, we will start with rearranging some of these. So what we'll do, we see that this is V average, this is V average. We're going to set those equal to each other because as you can see in this scenario down here, there is no V average. So let's get rid of V average by equating it. So we have V final minus V naught divided by 2 will equal delta x over t. So, and let's rearrange that because there's another thing that we need to get rid of. Now, this is a strategy that you can use when you're trying to prove or I guess trying to make a proof is find what is not in your equation. Like we found V average. V average isn't there, so we got rid of it by substituting it out with a whole other equation. Now, there is VF, V naught, there's even a 2 and a delta x, but the thing that's not there is this t. We don't want that t there. So let's solve this for t so that we can do something about that. So if we cross multiply, that'll get, and then we can divide over the v's. So I'll do that one step at a time. We've got t, no, that's not one step at a time, Pentecost. T times VF minus V naught equals 2 delta x. And you can see that that's pretty close to what we need, right? That's pretty close to our goal. Now let's solve for t so that we can get rid of it. That makes it easier to get rid of something. 2 delta x divided by V final minus V naught. Now, we've got one more equation. You can kind of treat this as an unknown idea. So you've got t as an unknown, so let's treat it as something that we can just get rid of. So let's solve this guy over here for t. So if t is in the denominator here, so let's multiply it over. Then you'd have a times t equals Vf minus V naught. Divide your a, got t equals V final minus V naught all over a, right? Now this is already getting messy, so I'm going to erase all of the work leading up to these two equations. But if you need to pause and take a second to catch up, go ahead and do that now. And I'll erase all of the work so I can get some room here. But what we're going to do is use these t's and get rid of them just like we did the average velocity. You can see we no longer have an average velocity. Oh, whoops, wrong button. Because we substituted it, right? So we want to get rid of this t, so let's substitute this for that t. So t equals 2 delta x over V final minus V naught. T also equals V final minus V naught over a. So that means that we can set those equal to each other. So let's do that over here. We have v final, whoops, this is getting messy, minus v naught all over a equals 2 delta x all over v final minus v naught. Now, I don't know how well you guys are at seeing the writing on the wall when someone's watching, when you're watching someone walk through some math, but here, if we cross multiply, we are almost done. So let's get rid of these guys, clear out some space to get some work done. So we'll cross multiply. Here we've got vf squared minus v naught squared. Actually, you know what? That's skipping a step, so I won't write it like that quite yet. We'll say we have vf minus v naught multiplied by itself, so that is squared, equals 2a delta x. The reason I put the a in that order is just because I see that that is the goal up there. Normally, if I multiplied 2 delta x by a, I would say 2 delta x a. But since I know you can always look back, what is your goal so that you can keep things in the right terms, keep it in the right verbiage so it's easily recognizable when you need to find what you're looking for. Now, if you have two terms subtracted within a parentheses squared, you can, if you FOIL that, you'll find that the middle term is going to get subtracted out. So I can't remember the name of that rule, but what you can do is you just square both terms, and it actually works out to be valid. So let's bring that down here. We've got vf squared minus v naught squared equals 2a delta x. If you guys can remember the name of that rule, I think it's something squares. But put that in the discussion, and I'll give you a stamp if you can give me the name of that rule. Where if you've got two terms subtracted in parentheses and square them, the middle term, because there's always a third term when you FOIL that stuff, it's going to go away. So now we just need to add v naught squared over to get our answer. We've got v final squared equals v naught squared plus 2a delta x. Whoops, don't cut off the answer there. And that is how you can prove that orange equation. That's the most complex orange equation that we have. We will get to the orange quad later. The orange quad is something special out of the orange equations, and we will talk about that next time in the next video. But this was a quick rundown over orange equations, what the three orange equations mean and why we have three instead of just one magic equation. And we talked about the limitations, constant acceleration, and that we're going to come back to that over and over throughout the entire course. So remember, if constant acceleration is in the problem, linear kinematics can work, or I guess one-dimensional kinematics can work. But if the acceleration is not constant, then we've got to do something different. Okay. And next video, we'll go over more of the orange equations, and then we will segue into the blue, and we'll discuss why we are not really going to use blue in this class.